electron configurations. And what is an electron configuration? What's the purpose of it? Why are we even talking about it? Yeah. Yeah, basically, where are these electrons inside the atom? Because what happens is maybe we can find some trends associated with this. Okay, and we had a filling pattern. They fill, what was like the first orbital we fill? Yep. 1s followed by what? Yep, then? Yep. Followed by? Yep. Yep. Then it gets weird. Followed by? Yep. 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 Oh, not 4p. 5p. My bad. Then? Yep. Yep, 4f.
We have a question. Why is 4 from 4d to 5p?
So why?
From 4d to 4p.
One more time, I'm sorry.
So you have it right now as 4d to 5p. Why does it not go from 4d to 4p to 5p?
Okay, well, like, why is it that way? Remember we talked about that electronic exchange and correlation. So as you start filling these orbitals, these energies get jostled around a little bit. Okay. The other thing is the lower energy orbitals, they're spread really far apart. The higher energy orbitals, the difference between the energies starts to shrink quite a bit. And then the orbital occupation really messes with those energies. Okay? It's about the best I can tell you right now. Okay, but we can represent these electron configurations graphically or written out. So, as an example, we're going to look at the simplest case. What is the electron configuration what's the simplest system you can think of in terms of number of electrons? Yeah. So we're going to consider and ask, what is the electron configuration of hydrogen? The way that we write out electron configurations, we tend to do this little bar thing, those types of parentheses. Then we have to indicate the types of orbitals and their occupation. What is the lowest in energy orbital we can have? Yes, specifically 1s, yep. We have 1s. Okay, how many electrons in total does hydrogen have? Yep, 1 electron. So what we do is we indicate its occupation, that orbital's occupation, with the superscript. So this is the orbital. And that's up here. This is the orbital occupation. We can represent this graphically. Represent this graphically. Okay, so what we do, we need an axis. We're going to label that axis with energy. Then what we're going to do, we're going to indicate the orbital we're looking at. What's the only orbital we have in this case? Yep, the 1s. We write 1s. We show that orbital with a line, and then we indicate its occupation. How many electrons can how many electrons can each orbital hold? You can hold 2, right? 1 positive 1/2 integer for the ms, negative 1/2 for the other part, right? So we're going to indicate that 1s is occupied with 1 electron. It doesn't really matter if it's spin up or spin down, but there is 1 electron in there. Okay, everybody sort of get this idea. Let's look at a more complicated example. Let's pick an element in the second row, one of the ones along here, which one do you want to do? What do you think? Anybody, whoever says it first gets it. Okay, carbon, we're doing carbon then. So let's look at the electron configuration for carbon. Am I okay to erase this? Same story. Another example. What is the electron configuration for carbon? Okay, first thing we have to know, what's the atomic symbol for carbon? See, good, you're alive from the neck up. Okay, we got carbon. How many electrons in total does carbon have? Yep, 6 electrons. Okay, now we need to start filling orbitals. What is the first orbital we're going to encounter? Lowest in energy. Yep, 1s. And remember, how many electrons can that s orbital hold? 2, yep. So how many electrons do we have left currently? Yeah, 4. What's the next orbital we're going to run into? Yep, 2s. And what's its occupation? 2, yep. Finally, last orbital, what do we got? 2p, and how many electrons are in there? Okay, I'm going to show you a little trick. You look at that periodic table. You ever wondered why it's organized in that fashion? Why does it do that weird step thing? So, how many, I'm going to draw this up, but you don't have to necessarily do it. How many columns are there in that like first S block? There are 2. Okay. What about over in the P block? How many columns are there? 6. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. How many electrons can the d orbitals hold again? In total? 6. How many can the s orbitals hold? 2. How many can the d orbitals hold? 10. If you count in that center part along here, how many columns do we have? Yeah, you got 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. What this is telling you is you can look and you can count. Basically, this should be up a little bit higher, I'm sorry. You can basically look and count. You can figure out the electron configuration based on this. So this element would have a 1s1. Sometimes helium is indicated over here or over here. We're going to do it this way, so it matches most periodic tables. 1s2. What about for lithium? What's going to be the highest occupied orbital? 2s, and what's its occupation? 1. Okay, what about the next guy over beryllium? 2s2, yep. Okay, now we jump over to boron. 2p, what's its occupation? 1. Okay, next for carbon. Yep, next. Yep. Yep. Last one. Okay, we can count, right? Good. You can know the electron configurations purely based off of the periodic table. All you have to be able to do is point and count. Each of the rows that we have, this indicates the n value, or the maximum n value. N is equal to 2. I didn't draw this quite right. This should be up a little bit more. We'll make n is equal to 3, huge. Actually, wait, n is equal to 3. Equal to 4. The only time things really change, so in this case, this would be potassium. What would be the highest occupied orbital in that case? Yep, 4s1. Next. 4s2. This is where it gets weird because there's going to be a shift. We're going to the p orbitals, right? Looking back at this filling, what's going to be the next highest occupied orbital? Yep, 3d what? 1, then 3d2, and so on. Now some of the transition metals, they get a little wonky. Things get weird precisely because remember when we talked about that electronic exchange and correlation, there's also something called Coulombic effects. Basically, there are quantum chemical effects that don't make it always follow this order. However, on an exam, I will only ask you elements that do follow this trend. Okay? So now we have a good idea of why the periodic table looks the way it does, but let's get back to our example. Let's draw out this electron configuration. Am I okay to erase this center part? Yeah? Okay. So let's draw the electron configuration diagram for carbon. Okay, we need an axis. What are we going to label that axis with? Or what's going over here? Yep, energy, right? Okay, what's the lowest energy orbital that we have? Yep, so 1s. And how many of those orbitals do we have? We have 2s orbitals, but how many 1s orbitals do we have? Yep. Okay. What about 2s? How many orbitals of that do we have? 1 again. How many p orbitals do we have for 2p? 3, yep. 1, 2, 3. Okay. Yeah. Okay, let's check that out. What we're going to do, we're going to keep track of our n, l, and m sub l value for each orbital we have. Okay, so what's n equal to for this 1s? 1. How about the l value? 0, m sub l value? 0. Okay, what about for this 2s? N is equal to 2. What's L equal to? 0, m sub L? Yep. Now, let's look at the P's. We know what their N value is going to be, right? What's their N value? 2. L value? 1. M sub L values? -1, m sub L is equal to 0, m sub L is equal to positive 1. The reason there are 3 p orbitals, there are 3 different orientations of this type of orbital, right? And based upon those quantum numbers that fall out of quantum mechanics, this is the diagram. Yep. Does that make sense? Okay, let's start filling electrons. So we got 1, 2, 1, 2, 1, 2. Okay? Now, and like when I ask you to write out the electron configuration, you don't have to indicate all of these quantum numbers, but just know these dashes, they're representative of the quantum numbers. Okay. Yeah?
Why would we put the T-space on what is it?
Let's talk about that next. Is there any other questions, John?
What are the things that you're putting on the line?
So these things, these are the electrons. These are like actually m sub s values. So like this would be m sub s plus 1/2. The one that's going down, we'll just say is ms minus 1/2.
So they're like arrows, kind of?
Yeah, they're arrows. They're half arrows. Like to try and show half numbers. Does that make sense? But they're corresponding to the spin of the electrons. Because we have to follow the Pauli principle. What did the Pauli principle state again? Had to deal with quantum numbers. So look back, tell me what the Pauli principle said. What's it say, guys? Yeah, they have to have different sets of quantum numbers. That's why we have the +1/2, -1/2. Okay, so now to get to your question, we have a couple set of rules that I didn't exactly talk about. So electron configurations. Must follow the Pauli exclusion principle, number 1. And what did we say that was, again, one more time? Yep, electrons must have different sets of quantum numbers. Okay. So let's look at the situation. You said why are they both spin up? Why are they in different orbitals? Let's talk about why they didn't occupy the same orbital. We have two possibilities. Which one's the correct one? The one on the left or the one on the right? Okay, this one is correct. Yeah. This one's incorrect. Let's, for argument's sake, let's pretend that this is a 1s orbital. And we're going to label these electrons. Let's label this one electron A, this one electron B, A, and B. So, what's my n value for this electron? 1. What's my L value? Being in an s orbital. 0. What's my m sub L value? 0. What's my m sub s value? Sure, we could be negative or positive. I like up being positive 1/2. What about so this is for electron A. What about electron B? On this side. Yep. Yep. M sub L? Yep. Okay, now let's look at the incorrect one. Let's try to determine why it's incorrect. For electron A, what's my n value? 1 L. M sub L? M sub S. Yep. What about electron B? N is equal to what? L? Yep. M sub L? M sub S. Right. So, why is this one incorrect? Yeah, they have the same set of quantum numbers. That violates the Pauli exclusion principle. That can't happen. But then if we look back to our p orbitals, we could have asked another thing. I did this, right? I did this, not that. Let's talk about why this one's preferred and that one's not preferred, okay? There's another rule we have to follow. Anybody know what it is? Starts with an H. Ends with an rule. Yeah, there we go. So we got the Pauli exclusion principle. Then the other thing is we have Hund's rule. And what that states is that electrons fill lowest in energy first, one electron at a time. So electrons fill, actually we should use occupy orbitals. One at a time. And they do not like to be paired. Okay, we'll talk about why they don't want to be paired, but let's look at two situations. We have a set of p orbitals. Let's do that one. Let's do that one. Which one's correct? The one on the left or the one on the right? Okay, yep, this one's correct. This one's incorrect. What do these dashes represent again? What's that?
Oh, the dashes?
Yeah, these.
I was answering like what the arrows.
Yeah, the arrows, those are the electrons, those half spins. But what are these dashes? They're the orbitals, right? So this is like an example of a px, this one's a py, this one's a pz, I don't know why I did x twice. Same thing with this guy, right? So remember, these orbitals have different orientations. One going out that way. Actually, we'll call that one P. Z, Px, and Py. Why is this one favored over that? Anybody have any ideas? Yeah. Yeah, that would mean that these electrons would be confined to the same space. And what do we know about electrons and their charge? Do they attract one another? No, they repel one another. It's repulsive, right? So we could either confine two electrons in one region of space, or we could confine them in two regions of space. Which one is energetically more preferable? Two regions of space. That's why this one is more correct. Does that make sense? Okay, keeping these two rules in mind, that's known as the Aufbau principle, where you're trying to fill electrons from low to high. All right? Any questions about that? Let's look at a tougher example, one that's similar to what you'll see on your daily problem. Okay, am I all right to erase this? Okay, we're going to do the electron configuration for a more difficult atom. The one we're going to look at is iron. So it's a transition metal. Geez, I'm drifting further away. So, example, electron config of iron. First thing we have to know, what's the symbol for iron? Yep, Fe. How many electrons in total does Fe have? Yep, 26. Okay, let's start filling orbitals. What's the first orbital we're going to fill? Remember, point and count using the periodic table. First orbital? Yeah, 1s, occupation. Okay, keep going. Not 3. How many?
2.
Yep. Oh. What's next? Yep. Next? Yep. Yep. Now we drop, yep. 4s2, we drop down a row. Now remember, what comes next?
3D.
Yep. 3D, and what is the occupation in this? this case? 6, yep. Because you look, it's in the 6th column over. 3d6. Now, let's try and draw the orbital or the electron configuration diagram. Again, we have our y-axis. What am I going to put as my unit for the y-axis? Yep, energy. Energy is going up. Okay, what is the lowest in energy orbital we have? Yep, it's the 1s. How many dashes do I need? Okay, next. How many dashes? Yep, next. How many dashes for p orbitals? 1, 2, 3. Yep, next. Yep. 1, 2, 3. Okay. Yep. Right. 1, 2, 3, 4, 5. And remember, what's the L value for a d orbital? Not 3. 2. So what are the values of n sub L you could have? Yeah, -2, -1. Yep, that's why there are 5 of them, right? Okay, let's start filling electrons. How many electrons do we have to fill again? 26. So remember, you start spin up. That one has as many spin up electrons as it can hold. So we do spin down, spin up, spin down, down, up, down. Okay, so now we arrive at the point where we have the d orbitals. How am I going to fill these guys?
One each, and then one other, and then another one.
Sure. That's completely acceptable. Okay. Any questions about that? Okay, I want to point something out. Your book does these incorrectly. So for example, we've been writing a p orbital like a 2p like this. Your book, it does this. Anybody know why the book is wrong? What can you tell me about the energy of these p orbitals? Yeah.
The energy doesn't increase within the orbital, it's just with the energy levels.
Yeah, basically. These are what's called degenerate. So these p orbitals are degenerate. Orbitals. These are orbitals of the same energy. Okay, so why does the book do them this way? Anybody have an idea? It's a real practical reason. Yeah, it's all about space. The more pages you have, the more the cost is, which is unfavorable, right? Okay, so keep that in mind. Ignore your book in this section. It's just wrong. Okay? All right. So we have this big, long string of things, but what we can do, we can actually write a shorthand for this, and that's known as a condensed configuration. So let's talk about those condensed configurations. Yeah?
How did you get 3d6 when 3p6? How do you get the 6?
Okay, so how did I get this 6 value? So if you look up to this point, if we add all of these occupations that I'm squaring, if you add that all up, what's the total you get? Yeah, you get 20, right? So we said our system, how many electrons does it have in total? 26. So the last 6 just have to go into the next available orbital.
Okay, so you don't write the 10 of the,
Right. The d orbitals can hold a maximum of 10, but not all atoms have a full filled 10 in their d orbitals. Does that make sense?
Yeah.
Any other questions? Good questions. Okay, let's talk about condensed configurations. So condensed configurations save us on time because there's some redundant information. We're going to discuss core and valence electrons. 2. Okay, so condensed electron configurations. Basically, these are, it's a shorthand way to write out the electron configuration. Or electron config. What you do, you find the nearest noble gas and you utilize its configuration. So use nearest noble gas. That's how you spell noble, right? You get Nobel and noble screwed up constantly. So let's use our example of iron again. Let's write out that complete configuration. We had 1s2, 2s2, 2p6, and so on. We just determined that. Okay. So now let's look at the periodic table. If you look at that periodic table, which noble gas, where are the noble gases located again? Yeah, the very last column, like, could you tell me an element that's a noble gas? Yeah, argon. Okay, now we need to look at iron. Iron's at atomic number 26 here. And we've got to find a noble gas that has that many electrons or less. What is the nearest noble gas to iron? Yeah, argon. Go back at that point. So what we could do, we could be lazy. Instead of writing this whole thing out, we could say, hey, it has the same configuration of argon, plus some other stuff. What is the other stuff that we're going to have here? Yep. Okay. You want to see another example of this, or do you feel comfortable with that? Yeah, let's do another one. Okay, let's do, pick a second row element. What's your favorite second row, or excuse me, third row element, like with aluminum, all that stuff? Okay, chlorine. Let's write out the complete configuration for chlorine. How many electrons does chlorine have? Yep, 17 electrons. So start rambling off the configuration. Yep. Yeah. No, you don't have to. This is just to keep track of your own. Like to make sure you're doing it right. Because if you add up all these occupations, it should be equivalent. Okay, next orbital. What do we got? Yep, keep going. Yep. Mm-hmm. Nope, not 4s. Yep, 3p. Count those boxes. What are we at? 5. Yep. Can anybody tell me the condensed configuration? What's the nearest noble gas? Remember, it has to have as many or less electrons. Argon has 1 more, so it can't be that. So what's it going to be? Neon, yep. What comes next? Yep. Okay. everyone feel comfortable with that? Know how to do that? Okay. Am I okay to erase this side? So let's talk about inner or core electrons versus valence electrons, because this is a topic, or at least a term we're going to use quite a bit, is valence and core electrons. Oops, we're disappearing. Wake up. So inner versus valence electrons. So inner electrons, they're usually not perturbed or involved with chemical bonding, usually. So inner, sometimes we use the word core, electrons are usually not perturbed and usually do not participate in bonding. Bonding. However, what do you know about valence electrons then? Yeah, they're the primary driving forces for chemical bonds. So participate in chemical bonding. Inner electrons, their configuration can be represented with a noble gas. So configuration represented by a noble gas configuration. So let's jump back to our example of iron. 1s2, 2s2, 3s2, 3d6, 4s2, 3d6. What I want you to do is I want you to pick out which one are the core electrons, which one are the valence electrons. Did anybody tell me a core electron or an orbital that has the core electrons? What was that? Yep, 1s is definitely a core. What else? Yep, 2s, what else? B, yep. Yep. Is that it? Yeah, these guys are the core electrons. They're really not involved in the bonding. What about the last two? Yep, these guys are the valence electrons, and those ones are usually involved with bonding. Okay? Any questions about that? Yeah.
So if you have a different element, would it always be true that the last two are always the valence electron?
No.
How would you?
So this could be represented, these core electrons, how could we express that configuration? What element has that same configuration? What was that? Yep, argon. Okay. You want to do another example? Okay. Pick an element that is fourth row or higher. Lithium? Okay, lithium. How many electrons does lithium have in total? Yep. Okay, tell me the complete configuration for lithium. So what's the complete configuration for lithium? Yep. S, what is it? 1, yep. Okay, tell me the condensed configuration for lithium. What's the nearest noble gas? Okay, we got helium followed by what? Yep. What orbitals are considered to have the core electrons? Yep. So those are the core electrons, leaving that 2s1 to be the valence, right? Make sense? Okay. Any other questions? John?
So in the example of iron, how are there 8 valence electrons?
How are there 8 valence electrons? If you add up the sum of just these two occupations, it totals 8.
So how does that, like, how do they even bond?
That is a tricky question because it's a transition metal, and we can't use like conventional, like if you're thinking Lewis dot structures where you just have to have 8 electrons around it and it's good. These guys do not follow Lewis dot structures. You have to look at something called molecular orbital theory to really check them out. There is a section in your book about octahedral complexes where, like for example, I'm going to draw something really weird. Where it's an octahedral complex. So the conventional ideas of like Lewis dot structures break down when you consider transition metal complexes. That's why we don't actually ever talk about them in this class. But if you're really interested, come to inorganic chemistry and we talk about it a ton. Okay. Any other questions? All right, have an awesome weekend. I'll see you guys around. Don't forget to check for your daily problem, okay? Good question, John.